Electromagnetism, or the electromagnetic force, is one of the four fundamental forces of nature. It generates light and energy and holds atoms, matter, and the world as we know it together. Electromagnetism is a branch of physics that studies the interactions between electric and magnetic fields. All matter has an electric charge, which can be positive, negative, or zero. Opposite charges attract, while like charges repel. These electric forces bring and hold atoms together. And when atoms gain a positive or negative charge through the transfer of electrons, a measurable electric field will form. If those electrically charged particles start to move, the field will become a flowing electric current and form a magnetic field around it. Under the right circumstances, interacting electric and magnetic fields can continuously produce and sustain one another. This generates an electromagnetic field that transmits waves of electromagnetic energy or radiation into space. The intensity of this radiation is determined by its frequency. These frequencies make up what's known as the electromagnetic spectrum. Near the middle of the spectrum is visible light, such as light emitted by stars, fireflies, and computer screens. On either side are invisible electromagnetic waves. On one end are long, low-frequency radio waves that broadcast television and radio signals, microwaves that carry telephone signals and cook food, and infrared waves emitted by fires. On the other are short, high-frequency wavelengths, ultraviolet, X, and gamma radiation. Unlike low-frequency waves, these waves can pass through the human body, making them useful for medical applications. While electromagnetism has daily applications, it's also the engine that drives the planet as a whole. Thousands of miles below the Earth's surface, a layer of liquid metals churn and flow. This generates electric currents that then produce magnetic fields that all together encompass the entire planet. Called a geodynamo, this process causes Earth's poles to attain positive and negative charges, turning the planet into a giant electromagnet. This phenomenon also creates a protective layer around the planet. It shields us from the most harmful radiation in space, leaving us to enjoy a world held together by the strange and fundamental force of electromagnetism.
The Earth's magnetism, or terrestrial magnetism. In 1600, William Gilbert, who was a physician to Queen Elizabeth I of England, showed that the force acting on a suspended magnet is not due to the influence of the pole star, but to a magnetic field which is present all over the surface of the Earth, as if the Earth was magnetized. Gilbert made a large spherical ball from magnetite, the poles of which were situated on two opposite ends. By placing a small magnetic compass on this magnetite sphere, Gilbert showed that the compass took up a definite direction at different points on the sphere as it does in the case of the Earth. According to his view, the magnetic field on the surface of the Earth can be approximately represented as if caused by a huge imaginary bar magnet in the interior of the Earth, but inclined to the geographic north and south axis of the Earth. This concept of terrestrial magnetism has been illustrated as shown in figure. The north end of the imaginary magnet has a south polarity, while the south end possesses the north polarity. Declination. In order to understand the term declination, let us first define two terms: geographic meridian and magnetic meridian. Geographic meridian at any place is a vertical plane passing through the geographic north and south poles of the Earth. Magnetic meridian at any place is a vertical plane passing through the magnetic north and south poles of the Earth. The angle between the magnetic meridian and the geographic meridian at a place is known as declination or variation.
So my name is Dr. Patrick Alkin, and I work in the geomagnetism group at the National Geophysical Data Center at NOAA. And one of the main tasks of our group is to produce models of the Earth's magnetic field. So the Earth's magnetic field is a big energy field. It's produced by many different sources. The primary source is molten iron, which is flowing around inside the Earth's core. And this creates electrical currents, which then create this big magnetic field which encompasses the planet. We created this data set, which is a magnetic declination data set, to kind of visualize how the magnetic field looks on different parts of the Earth and how you might use that for navigational purposes. At every point on the surface of the Earth, a magnetic field has a well-defined direction. However, if you have a magnetic compass, the compass needle will align itself in the direction of the magnetic field. But typically, that direction is not exactly pointing towards true north. So that angular difference between true north and the magnetic field is what we call magnetic declination. So the red and the blue just indicate the different conventions. So if you're standing in an area where the blue lines, we define that as negative declination, which simply means that if you have your compass needle would then be pointing toward the west of true north. And if you happen to be standing in one of the red regions, your compass needle would point eastward of the true north direction. And so we define eastward as positive declination and westward as negative. And so that's all the color scheme represents. And if you happen to be standing on the green line, then your compass needle would actually point exactly in the direction of true north. And so you get a zero declination in that location. And the time span of this goes all the way back to the year 1590, and it extends all the way up until the present day. And so back in 1590, primarily the people that were interested in magnetic declination were ships that were trying to navigate the oceans. So these ships would actually carry magnetic compasses with them and make measurements, and then they would need to correct that measurement with the local declination in order to understand what direction is true north so that they could navigate. In this animation, it shows you over several centuries how this declination is changing, but we don't really have a good understanding of why the magnetic field is changing, and it's very difficult to predict even just a few years in the future how what the field will look like. So for example, the green dot that's shown in the field of view right now is the magnetic north pole, and that is simply defined as the point where the magnetic field lines are vertical. And you can see that it's moving. For some periods of time it's very stable and it doesn't move that much. Other periods of time it moves faster. It's interesting because right now you can see that starting around the year 2000 it actually starts accelerating quite rapidly. So we don't understand exactly why this is happening. There are some scientists who suggest that we're in the early stages of a pole reversal. This is where the magnetic north and the south pole actually switch. And the last reversal was actually 750,000 years ago. And so you can argue that in kind of an average sense that we're overdue for a reversal. But of course we don't know for sure because we can't predict more than a few years ahead of time what the field is going to do. And so we need to kind of wait and see and improve our observations.
Dip. A magnetic dipole suspends freely at its center of gravity so that it can rotate about a horizontal axis. Suppose dipole takes up the position as shown in figure. The angle through which the end pole dips down with reference to horizontal is called the angle of dip. It varies over the Earth's surface. The places where the dip is 90 degrees north pole down and 90 degrees south pole down are called the magnetic poles of the Earth, generally denoted as NM and SM, along a line called the magnetic equator, which runs somewhere near the equator. The dip is 0.
In the previous classes, we have learnt about what is geographical north and what is magnetic north. In the slide given below, the line joining the poles of the Earth, that is North Pole and South Pole, is called as geographical north, or the reference line is called as geographical meridian. And if you freely suspend a magnetic needle, it will also show the north and south, and the lines joining these points will give you a direction which we call it as a magnetic meridian. The line joining the north and south pole of Earth is called as geographical meridian or true meridian. The line joining the north and south, which is shown by the magnetic needle, is called as a magnetic meridian. There is always an angle of difference between them, which we call it as a declination, which varies from place to place. And why the declination is changing from place to place, we have discussed in the previous video. Now, when it comes to the bearing, all that we do is find out the angle made by a survey line with reference to north. In the figure shown to you, there are 2 points. There are 2 survey stations A and B. We need to do the angular measurement. Why we need to do the angular measurement? In order to plot in a map, we need to have at least 2 measurements. The figure shows you the geographical north, and the angle made by the survey line with the geographical north is called as true bearing. In survey, the angles made with reference to the meridian is always called as a bearing. So the angle subtended by the survey line with the geographical meridian is called as true bearing. So as also we have magnetic north, so the angle subtended by the same survey line with reference to the magnetic north is called as magnetic bearing. So we have 2 bearings, which is true bearing and magnetic bearing. If you have a survey line AB, and if I insert a magnetic rose there, you can clearly see that the AB line subtends an angle of 45 degrees. So with reference to magnetic needle we are seeing, that is why this is called as a magnetic bearing. All the survey lines whatever we are doing the angular measurements are with reference to magnetic north. So we call them as magnetic bearing or simply bearings. In order to design or in order to notate the magnetic bearings, there are two kinds of systems. One is whole circle bearing system. Second is quadrantal bearing system. In the figure, let us say A is a survey point and B, C, D, E are the boundaries of a area. I have set up a compass at station point A and have started measuring the magnetic bearings to each and every line. The AB line magnetic bearing I have denoted AC, AD and AE. And if you set up the compass at that station point, you can clearly see the magnetic bearings. In whole circle bearing systems, the bearings are measured with reference to north only. Like I have denoted in the previous animation, you can see all these angles are measured with reference to north. So the angles with reference to north or the bearings with reference to north, if you denote it, then that system is called as a whole circle bearing system. In quadrantal bearing systems, we take the bearings either reference to north or south, like I have shown here. Our AB line lies in the quadrant A, northeast. AC line lies in the quadrant southeast. AD line lies in the quadrant southwest, and AE line lies in the quadrant northwest. In quadrantal bearing systems, we always denote the bearings either reference to north or south. So in whole circle bearing systems, the angles are from 0 degrees to 360 degrees, whereas in quadrantal bearing system, the magnitude of bearing is always 0 to 90 degrees and within the quadrant. There are three lines measured from the same point. One line is 66 degrees in whole circle bearing, next is 165, next is 330 degrees. Whereas if you measure the same angles in quadrantal bearing systems, we represent them with reference to the either north or south. For example, 65 degrees in whole circle bearings is referred as north-east 65 degrees, whereas 330 degrees is represented as northwest 35 degrees. We will see few problems in the next class. Thank you.